All right, so this is section 5.5 logarithms, but before I get started with logarithms, I'm going to talk about linear functions versus exponential. And I talked about this in the last video, but I just want to draw some parallels. So if we have addition in the linear world, that's multiplication. In the exponential world, subtraction. In the linear world is division. In the exponential world, we can have multiplication in the linear world. And the analog in the exponential world is powers. So just as an example, actually I do an example of this. Let's say a plus b, this is a times b. This is a minus b, this is a divided by b. This is a to the b, oh, sorry, no, this is a times b. This is a raised to the b. Technically, it could also be b raised to the a. We can have division in the linear world, and that is roots in the exponential world. So if we have a divided by b over here, then we have the bth root of a, which can be written as a to the 1 over b also. When we think about linear growth, that's exponential growth. And when we think about linear decrease, that's exponential decay. I think that's all that I can remember from lecture today when I previewed this. Okay, so linear functions start with addition, exponential functions start with multiplication. What we're going to see is that logarithms take exponentials and turn them linear. That's one of the big purposes of a log. So now let's jump into the warm-up, which looks like this, although I don't want to do exactly these questions, so come back over here. We've got 5.5 warm-up. So I might start with evaluate log base 3 of 81. So I think I showed this earlier, but I'm going to show it again. Let's give this an unknown variable like y. And now I'm going to rewrite this so that I can match it to the words I used. So if I have y equals log base 3 of 81, I would write y is the power that goes on. So this whole long phrase all corresponds to the symbol log 3 to get 81. And so you can match up all the terms with how you say it in your head or how you write it down. And then with that information, we say, okay, y is the power that goes on 3. So there's 3 to the y to get 81. So that's rewriting a log as an exponential. We've practiced that a little bit. So how many times do I multiply 3 by itself to get 81? You're welcome to use a calculator. I happen to know it's 4. 3 to the 4th equals 81. And log base 3 of 81 equals 4. That's kind of question 1. Let's just practice these a little more. Log base 7 of 49. So this blank space is the power that goes on 7 to get 49, and that power is 2. Because 7 squared equals 49. Log base 5 of x equals 9. That means 9 is the power. So 9 is the power that goes on x to get 5. And you could solve for x if you want, but that's not what we're doing right now. We can do more complicated things. They don't have to be that simple. We can do log of 3x minus 8 equals 14. When you don't see any numbers, you assume that's 10. So that means this number here is the power that goes on 3x minus 8 to get 10. And just as a reminder, when you see ln, that's the natural log. So natural log of 42 equals y says that y is the power that goes on the base. The base here is e to get 42. So if you're not super familiar with logs, just practice saying the sentence every time. 2 is the power that goes on 7 to get 49. 2 is the power that goes on 7 to get 49. 9 is the power that goes on x to get 5. 9 is the power that goes on x to get 5, and etc. That's our warm-up. Now let's talk about properties of logs. And this is where we're going to come back to this relating linear functions and the analog with exponential functions. And in particular, we're going to look at these three. Okay, so our first property of log says if I have a log of any base, so I'll use the base b, and I have two values in there and they're multiplied, I can write them as the log of that same base on b and a log of that same base on y. Here I have a multiplication inside of a log, and I turn it into an addition. Here I have a multiplication in the exponential world, and I turn it into an addition. So the way we have our log rules actually is reversed from this. So let me just rewrite it here. Exponential multiplication through the power of logs goes to addition. We also said that when exponentials are divided, that's like linears being subtracted. Put my base there. And we also said when exponentials are raised to a power, let's raise that to the power r, that's like a multiplication in our linear. So I'll do examples of all of these. We don't go through super precisely why these rules are true. If you remember that linear functions in addition correspond to exponential functions in multiplication, that subtraction in linear corresponds to division in exponential, and multiplication in linear corresponds to powers in exponential, that's going to be plenty. So if I have log base 3 of, let's look at a product, 9 times 27, that's the same as log base 3 of 9 plus log base 3 of 27. And if I want to actually go a little bit farther, this term, that's the power that goes on 9. Let me start over. I make mistakes, you have to deal with it. This term is the power that goes on 3 to get 9. Well, that's 2, because 3 squared is 9. And this whole term is the power that goes on 3 to get 27, which is 3. So over here on the right side, log base 3 of 9 times 27 is 5. And that's true because 9 times 27 is 243. And 3 to the 5th is 243. Log base 6 of, let's do 216 over 6. According to our log rules, is log base 6 of 216 minus log base 6 of 6. This term is the power that goes on 6 to get 213. That power is, or to get 216, that power is 3. Because 6 cubed is 216. This whole term is the power that goes on 6 to get 6. Well, that's 1 because 6 to the first is 6. And if I'm subtracting them, I get 2. And that makes sense because over here, 216 divided by 6 is 36, and 6 squared equals 36. So if you have terms divided, you can separate them out. All right. Log base, let's do 4 of 64 squared. Should be 2 times log base 4 of 64. Well, log base 4 of 64, this whole term is the number that goes on 4 to get 64. That happens to be 3. So 2 times 3, or 6. And that makes sense because log base 4 of 64 is the same, or 64 squared, is 4,096. And the power that goes on 4 to get 4,096 is in fact 6. 4 to the 6 equals 4,096. So those are the first 3 properties of logarithms: the product rule, the quotient rule, and the power rule. Here's a product rule where you're multiplying, here's a quotient rule where you're dividing, and here's a power rule where your term is raised to a power. There's some other rules. There's the one-to-one property, which says that if log base b of x equals log base b of y, then x has to equal y. Not all functions have the property where if the function outputs are the same, the inputs have to be the same, but logs are like that. So just as an example here, let me think. Log base 10 of, if I have log base 10 of 93 equals log base 10 of z, then z has to equal 93. And that's very handy because when you're solving equations, if you get down to where you have a log of something equals a log of your variable, then the inputs must be the same. And this is more one for practice to see how it works. Okay, there's the first power rule, which says any base raised to the first power is just that base. B to the 1 equals b. 3 to the 1 equals 3. 5 to the 1 equals 5. Right? We all know that. That we're comfortable with. How you write it as a log? Well, 1 is the power that goes on B to get you B. That's 1. 1 is the power that goes on 3 to get you 3. That's 1. So this right here is our first power rule. Anytime you see that the base is the same as what's inside the log, it's got to be equal to 1. And the last one is the 0 exponent rule. And that's just any base raised to the 0 power is 1. And again, we know that b to the 0 equals 1, 3 to the 0 equals 1, 5 to the 0 equals 1. So we write it as a log, and we say 0 is the power that goes on B to get 1. And 0 is the power that goes on B to get 1. Log base 3 of 1 equals 0. Log base 5 of 1 equals 0. Those are our 6 rules, the 3 on the other page, and these 3 right here. Moving on. A little more practice. This is kind of like question 1. If I tell you that log base 7 of 7 cubed equals something times log base 7 of 7, you should be able to determine that, oh, this comes from the power rule, and logs take powers and turn it into multiplication. 3 times log base 7 of 7. And let's just go ahead and finish this out. What power goes on 7 to get 7? 1. That's our first power rule. So we end up 3 times 1 or 3. Here's natural log of 32 minus natural log of 4. Logs, when they're linear, when you're subtracting logs, you divide the two. These are called arguments, what go inside the two arguments. 32 over 4 is 8. So if I wanted to really simplify, I could. And if I have, I'm just going to use natural log again because that's the simplest for me. Something, I don't know what goes in there, plus natural log of 5, and I know that's the same as natural log of 45. Then I must have something times 5 equals 45. Right, that's something times 5. Something times 5 equals 45, and that's 9. This is supposed to be natural log of 9 plus natural log of 5. It's a little bit of using those rules. I'm not going to do question 2 because I don't see any reason to put in a video of me doing things wrong on purpose. I'm just going to give you a hint. There are 2 mistakes in 5.5 question 2. All right. So I'm of mixed opinions about whether we need to expand logs, but it's certainly a good way to practice this. So let's just look at a natural log of 3u over z cubed times the 5th root of x plus 1. Ignore that thing. And we want to write this in the most expanded form. It doesn't mean it's simpler, it's just most expanded. So the first thing I would do is I would say, okay, I have a division in a log, goes to subtracting logs. So I have natural log of 3u minus natural log of z cubed times the 5th root of x plus 1. Now I have a couple different logs, and so here I have a multiplication in the log, and here I have a multiplication in the log. So I'll do both of those. When I have a multiplication inside of a log, the log turns that into addition. Don't forget, we're subtracting everything in here, so I'm going to put that minus sign with square brackets so I don't forget. There's a multiplication right there, so the log splits it into adding two logs, like so. This is done, but this has a power, and this has a power. So remember, the power says log takes powers and turns it into multiplication, 3 times log z. The fifth root is the same as the 1/5 power, so it's 1/5 x plus 1. That's as expanded as it can be. That's as expanded as it can be. That's as expanded as it can be. You notice the x plus 1, this is addition. But logs can't do anything to addition. They turn multiplication into division, but they don't turn addition into anything. So this is done here as well. And that's our answer. We are fully expanded. So if you're not sure why this can't be expanded more, that's a good time to review this list. Logs take exponentials and take multiplication to addition, division to subtraction, powers to multiplication, but there's no addition over here in exponential functions. So there's no way to go from addition inside of a log to anything else. But once you see just plain old addition inside of a log, you're done. All right. Let's do question 4. I don't know if I want to do question 4. Question 4 is similar to question 3. I'm not going to do question 4. Okay, so question 3 is about expanding. Now let's collapse a log. So this is kind of like question 5, collapsing logs. So suppose, I'm just going to use natural log again. I have natural log of u plus 5 natural log of x minus 1 minus 1/3 natural log of z. And I want to put that all into a single log. So I want to collapse it into one. The first thing I notice is I have 2 logs being added. Well, maybe I better start with this power. I have a, multiplication of a log there, and I have a multiplication of a log here. And so if I want to change this to multiplication and collapse it in, that turns into a power. So that's log of x plus 1 to the 5th. And this one is log of z to the 1/3. And I don't do anything with this one yet. I'm being patient with that. Now I have a bunch of logs where the coefficient on each is just 1. So it's safe to start combining them. So I have 2 logs added here. So I can collapse them into a single log where they're multiplied together. I can write this a cube root of z, but I'm not going to because I don't want to. Now I have 2 logs subtracted. So when I have logs subtracted, I can go into the exponential world where now I go from subtraction to division. So I have the log of u times x plus 1 to the 5th all over z to the 1/3, and I'm done. Now it's a single log with all the terms inside of it. And there's a couple more of those, and we're done. All right, video over.